In this unit, we're going to look at radioactivity or radioactive decay, and this is different because it involves the nucleus of the atom rather than the electrons forming chemical bonds. Remember, atoms form bonds to become more stable, and that's the electrons becoming more stable. But if the nucleus is unstable, then the nucleus has to change, and the nucleus changes in a process called radioactive decay. It's called radioactive decay because it emits energy, so the energy decays from the nucleus, but it could also emit particles. So it makes an unstable nucleus more stable by getting rid of that excess energy. And it involves the emission of energy or particles or both. Now, if it emits particles, it's also going to emit energy. If it just emits energy, no particles come out. This emission of energy or particles, this is called ionizing radiation. Ionizing radiation. Now remember, an ion is a charged atom, and atoms become charged by giving up electrons or gaining electrons. These things have enough, this ionizing radiation, these have enough energy to rip away an electron from an atom and change it into an ion. This can be harmful to you because you're made of atoms, molecules, DNA is a molecule that has the directions for your genetics, and if those get ionized or changed, it can result in bad, harmful effects. Okay. Materials that spontaneously emit radiation are called radioactive. So when we say something's radioactive, we mean the nucleus is actively giving off energy. Now, if it's also giving off particles, that's going to result in not only a more stable nucleus, but a nucleus that's different than what we started as. And if it changes to a different element, that's called nuclear transmutation. Okay? If it ejects particles, we get a new nucleus, and this changes it into a new chemical element. And that's nuclear transmutation. There's two processes that we're going to look at that lead to transmutation, and this includes alpha decay. Now, alpha is called alpha because it was the first one that was discovered, the Greek letter alpha. Then we had beta decay, and there's a third type, but it does not involve the emission of particles. So alpha decay, this is the Greek letter alpha. Beta decay, this is the Greek letter beta. It looks like a bee with a tail. And alpha looks like a fish. So we're going to have to look at these in a little more depth. So let's start with alpha decay. This is the emission of energy and an alpha particle. Okay. In alpha particle, it turns out is just 2 protons and 2 neutrons. Now, you should recognize that as a helium nucleus. Helium has 2 protons, 2 neutrons for a total of 4 things total. That's notation for the specific isotope of helium with 2 neutrons. Remember, 2 plus 2 is 4. The atomic number decreases by 2 because it loses 2 protons, and the mass number decreases by 4 because 4 particles are total lost from the nucleus. That gives us a new element. So if we think about an element that does this, uranium-238 does this. Uranium is element number 92. It has 238 particles in the nucleus. It actually goes through alpha decay, and so out of this we get a new element, and that new element's going to have only 90 protons. It's going to have only 234 things in the nucleus total, and if you look on the periodic table, element number 90 is thorium. And we also get an alpha particle, which is helium-4. Okay. Now you'll notice this adds up back to where we started. 234 plus 4 is 238, and 90 plus 2 is 92. So the total number of particles here hasn't changed, but we do have 2 different elements that we did not start with. Okay, so we can start with one element and end with another element, and this only occurs in nuclear changes. It doesn't occur in chemical changes. In chemical changes, the elements stay the same. Beta decay is a little bit different process. It also involves the emission of particles and energy, and it actually involves the emission of energy and an electron. Now remember, electrons have a negative charge, and this electron is spit out from a neutron, and that results in the neutron becoming positive. So if you think about this, we had a neutron that was neutral, and you can think of it as containing a proton and an electron together. And if that electron gets spit out, then this results in this thing being only positive, and we have a tiny little electron floating around. We also get out energy from this. Okay, so the atomic number is actually going to increase by 1 because we're going to end up with a neutron changing into a proton. So we gain a proton, and that's going to change the element into a different element. It is still decay, even though the number's increasing, because the amount of energy in the nucleus has gone down. Carbon-14 is an element that undergoes beta decay. So you start with carbon-14, and carbon is element number 6. So carbon has 6 protons and 8 neutrons, but it's got 14 total things in the nucleus. It undergoes beta decay, and that means we're going to increase the number of protons to 7. We still have 14 things in the nucleus. We didn't gain or lose any total particles. We just changed 1 neutron into 1 proton, and that makes this nitrogen. And we get out a beta particle. Now a beta particle is usually written as E, and this is 1 minus or minus 1, 0. Okay? That's an electron that came out of the nucleus. So we actually created an electron out of an electron and a proton from a neutron. The last type of radioactive decay is called gamma decay, and this is just the emission of energy. It does not involve the emission of particles. It's the emission of high-frequency electromagnetic waves. So these are actually more energy than X-rays. So if you guys remember, you have red light all the way up to violet light. Those are increasing energy. And then you have ultraviolet, that causes sunburns. Then you have X-rays, and those shoot through your skin and get stuck by your bones. And then you have gamma rays, and these have enough energy to, well, they're used to actually kill cells in radiation therapy. So gamma rays can be pretty nasty. So that's what this image shows here. Alpha decay involves the emission of some energy in these particles, and they hit a sheet of paper, they stop. So alpha decay can be blocked by clothing. It's a pretty big particle, so it's easy to stop. Beta decay, with just the emission of this high energy electron, is actually a little bit harder to stop, but aluminum foil will stop it. So it's still not incredibly hard to stop. Gamma radiation, though, gamma radiation is a little bit harder to stop. Since there's no particles there, it's just high energy waves. It needs a pretty dense material to go through it, and usually lead is used to shield for gamma rays.